Okay, so buckle up, Buttercup. We're getting ready to talk about particle classification and conservation laws. It's a little thick, there's a lot to keep straight, and some bookkeeping. It's not mathematically very challenging, but it can be a little confusing, so don't hesitate to stop, replay certain things, or make sure and also to read the textbook very carefully in these sections. So when you classify particles, there's two very broad categories, and they are classified by the type of interactions that they have with one another. So the hadrons are a group of particles that interact through the strong force. That means basically that they're composed of quarks. All right? Leptons, they interact through the weak force. Leptons are not composed of quarks. Remember, leptons are fundamental particles in and of themselves, as we'll talk more about today. So the hadrons, there's actually two subclasses for the hadrons, which interact through this strong force. These are the mesons and the baryons. Among the mesons, they have integer spins of 0 or 1. All mesons are inherently unstable, and they're not abundant in nature because they don't have very long lifetimes. When they usually decay finally into electrons, positrons, neutrinos, and photons. Baryons, also hadrons, they have masses equal to or greater than a proton. They have half-integer spin values, so they're fermions, and they decay into end products that include the proton, which of course, except for the proton. The proton is the only stable baryon. None of these, mesons or baryons, are elementary. They're composed of quarks, which we'll cover in a later lecture. There's a chart from another book that is not an exhaustive list, but does cover a lot of the common hadrons here. And you can see that it's separated into two classes, the mesons and the baryons. All right? So these interact through the strong force, they're composed of quarks, and you have them both here in one chart. But in case that's a little small, you also have the charts from your own book. So here's some selected mesons. Remember, these are the integer spins, 0 or 1. They're bosons, they're unstable. Let's look at some of them and discuss what their names are. So here you have these pi's. You have pi plus and then the pi 0. These are your pions, okay? These were found to be the mediators of the nuclear force. Then you have your K particles, your K plus and your K 0. These are called the kaons. Then you have your eta particle here, and then you have your rho and your D and your J psi particles, and so on and so forth. So they have some really interesting names. Note here that they have the mean lifetime in this chart, typical decay products, and also strangeness, the strangeness number, which we'll get to in a minute, in addition to the spin and the charge. Notice that they're all integer spin with spins of either 0 or 1. I should also note that if you have the particle listed in the leftmost column, the antiparticle will, of course, have the opposite charge that's listed here, okay? Now here's the baryons, okay? This is, again, probably not an exhaustive list, but you can see some of the typical ones here. These have masses equal to or greater than a proton with half-integer spin values, either 1/2 or 3/2, as is indicated here in the fourth column. They're fermions. They decay into end products that include the proton, of course, except for the proton, and the proton is the only stable one. The decay products are listed here. You can notice that the typical decay products are listed. There's nothing listed for the proton. It's the only stable one. Some of the ones that we see here, of course, the proton, the neutron, the lambda, the sigma particles, the deltas, the omegas, and so on and so forth. Okay. Now, the next class of particles, not hadrons, all right, we're out of the hadrons. We're moving into the leptons. The leptons do not interact through the strong force. They all have spins of 1/2, so they're all fermions. They appear truly elementary. What that means is that you'll never really be able to measure the diameter of an electron. As far as we know, it's a point particle, just like the muon is, and the nu, and the tau. They're all point particles, which is kind of hard to think about, especially for some of the ones that are more massive, but there you have it. You can measure the diameter of other things. For example, people have estimated the diameter of the proton. Scientists currently believe that only 6 leptons exist, along with their antiparticles. So there's the electron neutrino, the muon and its neutrino, and the tau and its neutrino. So here you'll see some of the mean lifetimes and some of the typical decay products. You'll notice that there's a lot more stable leptons than there are baryons or mesons. You can see that the mean lifetime of some of these things, like the neutrinos all have infinite lifetimes, so they're stable particles, and then the electron is a stable particle. So each of the charged particles has an associated neutrino. So there's the electron and the electron neutrino, or the muon and the muon neutrino. When the muon decays into an electron, because it's not a stable particle, and the tau, it'll decay into the electron. A muon or even hadrons can decay into products that include the electrons and neutrinos. Anytime you see a neutrino, you know that there's a decay going on via a weak interaction. So here's the muon decaying into an electron, a muon, and an anti-electron neutrino. So the neutrinos, we're already familiar with talking about the neutrinos from the beta decays in chapter 12. But neutrinos are really, really super interesting. I'm going to include a minute physics video about neutrinos that you should watch. They have zero charge with these tiny little masses, and the precise mass may have actually a bearing on current cosmological theories of the universe because of the gravitational attraction of that mass. All leptons have spin 1/2, and 3 neutrinos have been identified experimentally, and they're difficult to detect, particularly difficult to detect, because they have no charge and very little mass. So they really only interact with things via the weak force and gravity. All right, now there's a number of different conservation laws that are important when you study elementary particles. We've already seen conservation of energy, linear momentum, angular momentum, electric charge, and of course those conservation laws still apply. But we're going to learn 3 new conservation laws today that are important in particle physics. And those are conservation of baryon number, conservation of lepton number, and then conservation of strangeness. So first let's talk about baryon number. We already talked about the baryons, a class of particles. So baryons have a baryon number. Whenever a baryon is created in a reaction or a decay, an antibaryon is also created. I'm going to go with B for the baryon number. Your book uses L, but we've got so many L's, I just get tired of it, okay? So I'm going to go with B in my lecture, all right? So B is equal to +1 for the baryons, like the proton and the neutron. And B is equal to -1 for the antibaryons. Remember, every particle has its associated antiparticle. And B is equal to 0 for all other particles. So in a reaction, in a particle physics reaction, the sum of the baryon numbers before the reaction or decay has to equal the sum of the baryon numbers after the decay. Now currently there's no known violations of baryon conservation, all right? So anytime you have a problem that you're going to do for modern physics right now, you need to assume that baryon number is conserved. But perhaps, maybe, it was violated in the early universe, which would help explain the prevalence that we have now for matter over antimatter. There's a debate, a current debate, over whether the proton is actually going to decay or not. Your table lists the lifetime as infinite, but it's actually estimated that the proton has a half-life of at least 10 to the 33 years. And this is predicted by some recent theories which predict that the proton is unstable, and so that the baryon number wouldn't be absolutely conserved, that it might be violated. It just doesn't get violated very, very often because the half-life is so very long. 10 to the 33 years is longer than the age of the universe. And if a proton decays in a forest, but its half-life is so long that it's longer than the age of the universe, does it really matter? Get it? Matter? Okay. Sorry, it's a bad joke. Just trying to lighten the mood a little. Okay, so let me do an example of baryon number conservation. So is baryon number conserved in the following reaction? Now remember, reactions, nuclear reactions, particle physics reactions, they're written out like chemical reactions are written out, where you have the products, the reactants on the left-hand side and the products on the right-hand side, and an arrow in between. So here we have a proton plus a neutron, yielding a proton plus a neutron plus an antiproton. So let's figure out whether we think this is going to violate baryon number conservation. So protons and neutrons are baryons, so they have baryon numbers of +1. So on the left-hand side, you have a proton and a neutron, which is a baryon number of 1 + 1, which would equal 2 for the baryon number on the left-hand side. Now, on the right-hand side, you have 2 protons and a neutron. That's 1 + 1 + 1, which is 3. And then this bar above the top, that's common notation for the antiparticle. So this is an antiproton. And antibaryons have a baryon number of -1. So you have 1 + 1 + 1 -1, which gives you 3 - 1, which is 2. So that means that on the left-hand side and on the right-hand side, the baryon number is 2, so the baryon number is conserved. Now you might also be looking at conservation of charge. Charge conservation is very important in these reactions too, and you need to check it. So on the left-hand side, the neutron is neutrally charged, so it has a charge of 0. The proton has a charge of +e. Now on the right-hand side, you've got 2 protons for +2e, and then the neutron, which is 0, and then the antiproton would have a charge of -e. So you have 2e minus e, which is e. So charge is conserved for this reaction. Therefore, the reaction can occur as long as energy is conserved too. Now, you can't really write into these reactions whether or not energy is conserved. What happens here, remember from Modern 1, that you can create mass energy if you have enough kinetic energy. And that's what they do at CERN all day long and twice on Sundays, right? They have these particles that they hurtle at super high speeds, close to the speed of light, towards targets. And that high kinetic energy during the reaction when it hits the target can be converted into mass energy. And that's how they create all those crazy particles that you see. Okay, so when this reaction is written out, you just kind of have to take for granted that the kinetic energies of your reactants on the left-hand side are really high enough maybe to create all these particles on the right-hand side. And sometimes you might even have to solve for what the kinetic energies of these particles must be in order to create all the particles on the right. Okay, the next conservation law is the conservation of lepton number. So we have conservation of baryon number, and we have conservation of lepton number. Now, I'm kind of fibbing here. It's not really one conservation law. It's actually 3, because there's 3 varieties of leptons. There's the electron, the muon, and the tau, and their associated neutrinos. So what has to happen is you have to have conservation of electron lepton number, which means that your electron lepton numbers before have to equal the electron lepton numbers after. And then you also have to have conservation of muon lepton number and tau lepton number. Okay, so when you conserve lepton number, you're actually conserving 3 types of lepton numbers. So what we're going to do, I'm going to go with your book's notation for this because at least they put a subscript after it, L sub E, for electron lepton number. Okay, so anyway, for the electron and the electron neutrino, you have an electron lepton number of 1. For their antiparticles, the positron and the electron antineutrino, your electron lepton number is -1. And then for every other particle in the world, it's 0. Okay, and that's a similar process for muons. Muon lepton number has to be conserved, and taus, the tau lepton number has to be conserved. And the notation would be the same, okay? Except the subscript would be a mu and a tau for the muon and tau muon and tau lepton numbers respectively. Okay. So let's look at this reaction for an example. Is lepton number conserved in this reaction? Here you have a muon decaying into an electron antineutrino, and a muon neutrino. So let's check this out. Okay, so before the reaction on the left-hand side you have a muon. That makes the electron lepton number equal to 0. Now after, your electron lepton number is 1 for the electron, and then this is the antineutrino for the electron. So that's going to have an electron lepton number of -1. Okay, and then the muon neutrino here has an electron lepton number of 0. So you have 1 minus 1 is 0. So that means electron lepton number is conserved in this reaction. You also have to check the muon lepton number. Okay, so before you have a muon, so that's got a number of 1, And then after, the electron and the antineutrino for the electron, those both have muon lepton numbers of 0. And then you have your muon neutrino here, and that has a muon lepton number of 1. So you have 1 on the left-hand side and 1 on the right-hand side, so muon lepton number is conserved. Now, you might have had your ears perk up a little bit when I said strangeness earlier, okay? So strangeness is an entirely new concept. These particles were actually discovered in the 1950s, so we're getting really recent in our physics now. And they were found to exhibit unusual, strange properties in their production decay. And so because physicists aren't very creative sometimes, they called them strange particles, all right? Just because they behaved in a strange way, they were named strange particles. The peculiar features, because let's not be redundant and overuse the word strange, right? So the peculiar features include they're always produced in pairs, and although they're produced by the strong interaction, they don't decay into particles that interact via the strong interaction. When they decay, they have to decay via the weak interaction, so that made them strange too. They decay a lot more slowly than particles that are decaying via strong or electromagnetic interactions. We'll talk more about that later in this lecture. And since they're produced by the strong interaction, there are no strange leptons. There's only strange hadrons. All right, so strangeness does not exist for the lepton family. So to explain the unusual properties, they had to introduce a new quantum number. And I'll call it S, just like your book does. And it's called strangeness. All right, and this was introduced, and they had to introduce a new law, the law of conservation of strangeness, and that was also necessary. Now, if you've been paying attention in Modern 1 and Modern 2, you might be thinking that strangeness has been conserved all along, that strangeness was in fact created in Modern 1 and just continues through to now, okay? But that's not the kind of strangeness we're talking about here. Basically, the law of conservation of strangeness states that the sum of the strangeness numbers before a reaction or a decay has to equal the sum of the strangeness numbers after the process. Now, the strong and the electromagnetic interactions, they obey the law of conservation of strangeness. But the weak interaction is pretty strange itself. So it can actually violate strangeness conservation, but only by a little bit. The strangeness number can only change by plus or minus 1 when the weak interaction gets involved. So, reiterating, strangeness is conserved in strong and EM interactions, but not in the weak. Now, looking at some of the particles that we've talked about, the kaons, the K particles, they have a strangeness of plus 1. Your lambdas and your sigmas have a strangeness of minus 1. Your xi has a strangeness of minus 2. And your omega is super strange, and it has a strangeness of minus 3. When the strange particles are produced by a strong interaction, often by slamming 2 protons together, they have to be produced in pairs, because otherwise strangeness isn't conserved. All right, here's an example, a picture, if you will, of a bubble chamber where some strange particles have been created. Now, what impresses me about this is that physicists at the time actually took these traces, studied them for a really long time, and then based on the trajectories and the radii of these circles as they move through the magnetic field, they could figure out what the heck was going on. I'm not sure I could have done that in 1930. I'm pretty impressed. Anyway, the dashed lines in this figure represent neutral particles. Now at the bottom, there's this little area that has been zoomed in on, and you have this cool little pathway going on here where they figured out what all these particles are. And so here's the reactions. You have a pi meson plus a proton busting into each other and creating a kaon and a lambda particle. And then that lambda particle subsequently decays into a pion and a proton. And your kaon subsequently decays into the antiparticle of the pion, a muon, and the muon antiparticle neutrino. So that's what's going on. Now, let's figure out this strangeness conservation thing by going through these 3 reactions and really analyzing them in detail so we can figure out what's going on here. So first of all, here's your production reaction. You have a pion and a proton slamming into one another, creating a kaon and a lambda particle. Okay, so that's a production reaction. You can tell it's a production reaction because you have two particles on the left-hand side, okay, and they're creating two different particles on the right-hand side. Now let's look at the strangeness number and the baryon number for this top reaction. Okay, now on the left, you have your pion and your proton, and those are not strange. So your strangeness number on the left-hand side is 0. Now on the right-hand side, though, and you can see what the strangeness numbers are by reading them off the chart in those tables in your book that I've shown you in the lecture already. The kaon here has a strangeness of +1, and the lambda particle has a strangeness of -1. So this is what I mean when I say they have to be produced in pairs. You have one with a strangeness number +1, one with a strangeness number -1, giving you a total strangeness number of 0. So strangeness for that reaction is actually conserved. That makes it an interaction via the strong force because remember the strong force has to obey strangeness conservation. Now let's also look at the baryon number conservation. There's no leptons here, so we don't need to worry about lepton number conservation. That's trivially 0. But let's look at the baryons because there are some of those. Your pion, that's not a baryon, it's a meson, so its baryon number is 0. Your proton has a baryon number of 1. Your kaon, that's also a meson, so its baryon number is 0. But your lambda, that's a baryon, so it has a number 1. So you have 1 equals 1, so baryon number is conserved. All right, let's look at the next one, okay? Here you have a lambda particle, and it's actually decaying into a pion and a proton. Now you can tell it's a decay because it's a decay when you only have one thing on the left-hand side, all right? Now decays are the ones where you really have to look out for the weak interaction taking a role and the strangeness number changing by plus or minus 1. Okay, so here we go. Your strangeness of that lambda particle is -1. Your pion, it's not strange, it's got a strangeness number of 0, and neither is your proton. Okay, so your strangeness number goes from -1 to 0, so it's increased by 1. So your delta S is equal to +1. That means the weak interaction is in play here, all right? And strangeness can be violated by plus or minus 1. Now, your baryon number is also conserved. We kind of talked about this above. So you have a lambda, which has a baryon number of 1 on the left, pion, nothing, no baryon number. On the right, a baryon, so 1 equals 1, so baryon number is conserved. All right, let's move on to this third reaction. Here you have a kaon decaying into a pion, a muon, and then the anti-muon, the antineutrino for the muon. So here, the strangeness number for the kaon is +1, but the strangeness number for everything on that right-hand side is 0, okay? Muons and the neutrinos, those are leptons. They're not strange because they're leptons. And then the pion, as we've already discussed, has a strangeness of 0. So that means your strangeness number has gone from +1 to 0, so that means it's dropped by 1. So delta S is -1. Okay, so yet again, this is a decay, and oftentimes decays are dictated by the weak interaction. Many decays are, and so you see that you have a delta S of -1 via the weak interaction. Now, here you have some leptons, so let's go through lepton number. The kaon, not a lepton, its lepton number is 0. Pion, also not a lepton number is 0. Here you have your muon. It has a muon lepton number of +1. And then here you have the antineutrino for the muon, and it has a lepton muon number of -1. So you have 0 on the left-hand side equaling +1 -1, which is 0 on the right-hand side. So lepton number is conserved. All right. There you have it. You can also look at conservation of charge in each of these reactions, okay? If you look at the top reaction, your pion here is a negatively charged pion. You can tell that by the superscript. And your proton is, of course, positively charged. So -1 + 1 is 0. And then these 0 superscripts on the right-hand side mean that they're neutrally charged. So you have 0 charge on the left and 0 charge on the right, okay? If you look at the second reaction, your lambda particle has that 0 superscript. You know it's neutrally charged. The minus sign here indicates a negative charge. The proton is positive, so you have 0 is equal to -1 + 1, charge conserved. Kaon here, 0 superscript, neutrally charged. Positive pion here, negative muon, and neutrinos have no charge. So you have 0 is equal to +1 - 1, charge is conserved. So these are some of the charge, lepton number, baryon number, and strangeness conservation rules that you have to check for these reactions. All right, now here you can look at some of these charts that I talked about earlier, and let's examine them in a little bit more detail and talk about certain highlighted points on this, okay? Now, if you look at the decay mechanisms for the pi 0 here, the pion, pi 0, the neutrally charged pion, and the eta particle, in the right-hand column where it shows the typical decay products, you can see that both of those particles decay into 2 photons, okay? They can decay into the 2 photons by the strong and electromagnetic interactions, all right? They have very short lifetimes, 10 to the minus 17 and 10 to the minus 19 seconds, okay? That is typical of strong and electromagnetic decay pathway times, okay? They have short lifetimes on the order of, within a few orders of magnitude, 10 to the minus 20 seconds. So very, very short lifetimes. Now look at this kaon right here, this K positive pathway, okay? Its lifetime, however, is kind of long compared to the other ones. It's about 10 to the minus 8 seconds, and it decays into a muon and a neutrino, okay? So that is the lightest strange particle. If you compare the K plus to the K0, for example, then you can see that the rest energies are 494 and 498 MeV. And if you were to look at the next chart with the baryons, you would see that K particle there, that is the lightest possible strange particle. So the kaon really can't go anywhere. When it decays, it has to decay into something using the weak interaction, okay? Because it can't decay into anything else strange. It's less massive. It's the least massive. And anytime you have a weak interaction decay, the lifetimes are going to be longer because it takes a long time if you want to violate some conservation laws, I guess. And so those have the order of 10 to the minus 8 seconds. You'll also notice that this pion, now it's not strange, but its decay time is 10 to the minus 8 seconds. And look, it's decaying into a muon and a neutrino, okay? So those longer lifetimes, 10 to the minus 8, 10 to the minus 10 seconds, and the presence of those neutrinos, they indicate that the decay is via the weak interaction, okay? Okay, so if you see a short mean lifetime, 10 to the minus 20 seconds or so, that's a decay via the strong force or the electromagnetic force. If you see a longer lifetime, about 10 to the minus 10 seconds, that's a decay via the weak force. The weak force can violate conservation of strangeness, and it's also a symmetry breaker. It's allowed to break other symmetries. So if you see here, you see this long lifetime for the neutron, and you see some neutrinos, that screams weak interaction, okay? Now some of these guys, they don't have neutrinos in them. They have pions and things like that instead of neutrino, but you can still look at the lifetimes for these guys, the lambda and the sigma particles, and you can see that it's 10 to the minus 10, 10 to the minus 11 seconds, okay? Also, if you look, the lambda and the sigma have some strangeness to them, whereas the decay products have no strangeness, so that screams weak interaction as well. Here's a 10 to the minus 20 second lifetime, and it's decaying into another particle that has some strangeness in it, so that's a strong interaction decay. And then all these guys, 10 to the minus 10 seconds, those are weak interaction decays, and so on and so forth, okay? Again, here's the chart. Anytime you see a neutrino, you know weak interaction is responsible for the decay. If you see 2 photons, it's probably the electromagnetic force that's causing that decay, and they have those short lifetimes like the strong force decays. Pions or mesons, they don't change conservation of baryon number, lepton number, or strangeness. So you're going to see lots of pions in these charts. You can actually add in as many pions as you want as long as you have the energy necessary to create them. So that's kind of an interesting little factoid about the pion. So to sum up for the conservation laws covered today, here they are listed in your as according to the words in your book. In any process, the total baryon number must remain constant. Baryon number conservation violation doesn't happen. In any process, the lepton number of each type of lepton must remain constant. Again, lepton number conservation violation doesn't happen. Number 3, in processes governed by the strong or electromagnetic interactions, the total strangeness must remain constant. In processes governed by the weak interaction, though, the strangeness either remains constant or changes by only 1 unit, okay? So strangeness conservation can be violated, but that screams weak interaction, and it can't be violated a lot. It only can change by plus or minus 1. All right, so hopefully you understood, and if not, make sure to read the book, go back and replay certain sections, and I'm also happy to answer any questions you might have.